Hello everyone, in this video we're going to look at the lesson 12 accounting real quick. Point 8 is one sample, single proportion test. For single proportion test, if it's a small sample, we use binomial distribution to find the p-value. If it's a large sample, we use z-score, we'll use proportion test, z equals p minus p0 over square root of p0 q0 over m. This is normal distribution if if n is big. If n is small, we have to use normal distribution. Sorry, binomial distribution. Okay, so we can look at this example 10.10, and a commonly prescribed drug for relieving nervous tension is believed to be only 60% effective. So we got P equals P0 equals 60%, 0.6. Experimental result with the new drug administered a random sample of 100 adults. N equals 100 is bigger than 30, so we can use normal distribution now. Who are suffering from severe nervous tension shows that 70 people received relief. So I got X equals 70. And then the experiment data gave you P equals 70 out of 100, which is 0.7. Well, to my opinion, 0.6 and 0.7 are really close, but it's kind of like I don't know. If you say, oh, it's 0.61, if it's 0.61, yeah, it's close. 0.62 is still close. But whether it is really close, or is it superior, we don't know yet. We have to use the hypothesis test. Okay, so for example, recently, if you pay attention to the news of the president poll, they said the polls of that, they said the vote is biased when it's kind of like people says, okay, if you use the in some district, the people use the computer or use paper, they have like significant lower level. Okay, I think they use the hypothesis test to claim that it's significantly lower than the people use the paper way to vote. Okay, so but that's not related to our class, but I think they use this knowledge to do it. Right, so now let's back to here. So P equals 0.6 and the experiment data is 0.7. So we use the z equals z equals p minus p square root of p0 is what you claim for hand. So equals 0.7 minus 0.6 square root over 0.6 times 0.4. Because p0 equals 0.40, so q0 is 0.4. Okay, and over 100, you find the z-score is 2.04. So if z equals 2.4, now let's find z bigger than 2.04. So it is less than 0.0207. So it's very small. Okay, so now the proportion claim value P equals 0.6 is right here. And now I got this value is almost here, so it's really far away. This right here, P is 0.6 is here, right? I got Z score is almost here. Z is 2.04, but you can see there's only 0.02% right here. So it's really far away from the P equals 0.6. So now I have to reject the null hypothesis. P is small, P is low, the null hypothesis must go. Okay, so P value, P is low, like null hypothesis must go. So this 0.02 is really small. So I think it compares with the 0.05. Is lower than 0.05. So the null hypothesis must be go. So I have to reject null hypothesis, which means I have to claim that the new drug is superior. Okay, so for two samples, test on two proportions. Two proportions, you're going to have very similar methods to do it, but you have used a different way to find the z-score. So P1 minus P2 minus P1 minus P2 over square root of P1 Q1 over N1 plus P2 Q2 over N2. Use this formula to find the z-score, and then use the normal distribution find the probability. Okay, so this is the example 10.11. You can look at this example. In the homework, I'll introduce how to use the StatCrunch to do the problem as well. And then I don't think it's really hard. You just plug in the values into the formula, find the z-score. Once you find the z equals 2.9, then you use that table to find out z bigger than 2.9 is very small, 0.0019, and p is small, p is low, and the null hypothesis must go reject null hypothesis. So that's 10.9. 10.10 is 1 and 2 sampling concerning variance. So the variance we are going to use F distribution, I think. Okay, so basically what we're going to do, we're going to use the null hypothesis if this section introduced if the two sample or one sample have the same variance, if the variance are the same or not the same, if one variance is bigger than other variance. So we know that chi-square equals n minus 1 square. Okay, n minus 1 square over sigma square. This is the chi-square distribution. The ratio of two chi-square distribution is going to be the F distribution. Okay, so for example, a manufacturer car battery claimed that the life of company's battery is approximately normal distribution with a standard deviation equal to 0.9. And if a random 10 of this battery standard deviation is 1.2, and you think that sigma is bigger than 0.9, so basically now the null hypothesis is sigma square equals 0.81, and alternative hypothesis sigma square is bigger than, because it's bigger than 0.9, square is bigger than 0.81. So what do we do? Alpha is 0.05. We can have chi-square distribution equals n minus 1 s square over sigma square. And then we can find out the chi-square equals 9 times 1.44 over 0.81. Then this is 16.1. And you got a chi-square at the V freedom of degree is 10 minus 1 equals 9. Use the table, freedom equals 9, and the chi-square is 16.1. And the area here is 0.07, which is small, which is very small. Wait, the null hypothesis is not small. It's compared with the 0.05, it's bigger than. So the p-value is high than the null hypothesis flies. So wait, it's not significant. We got that is p is 0.07. It's not significant at 0.05. So based on the p-value is 0.05, that the evidence that sigma is bigger than 0.9. Okay, so if p is 0.07, if you compare with the 0.05, it should be bigger than 0.5. Okay, but it's still considered very small. And it says reject the null hypothesis, but it's really close to 0.05. Okay, normally, if it's bigger than the significance level, then we will not reject the null hypothesis. So let me say, continue read the problem. Consider the problem testing equal. Okay, so the first one, if you claim that sigma square equals 0.81, then it's one sample, you use chi-square. If it's two samples, sigma 1 square over 2 sigma 2 square, you're going to use chi-square. The chi-square you're going to have, if it's a ratio of this sigma square, it's going to be an F distribution. Okay, so for independent random sample size n1, n2 respective for two populations, F value is testing sigma 1 square equals sigma 2 square. And what we have is we still have the same. Look at the example 10.13. Then testing for difference in the abrasive wear of two materials in example 10.6. Assume that two unknown population variants are equal. unknown. So sigma and sigma 2 unknown. We justify making this assumption. So null hypothesis is always equal sigma 1 square equals sigma 2 square. Alternative hypothesis is sigma 1 square not equal sigma 2 square, and alpha equals 0.1. So what do we do is the 0.1, so F distribution is it's two-sided region. So it's going to point the one side is 0.05, the other side is 0.95, and we find out 11, 9, and equals 1 over F 0.05, 9, 11. Okay, this is the formula of F distribution. So what do we do? We find the F distribution. The F distribution is 16 over 25. I think the previous example it's given to you 16 over. There's another example give you S1 and S2. Okay, S1 square is given, S2 square is given. So find F distribution, find both of them, and find F decision. Do not reject the null hypothesis. Conclude that there is insufficient evidence that the variance are differ. Okay, so in the homework, I'll introduce how to use the calculator to do this work, to do the F test. 10.11 is good list of fit test. So good list of fit tests, basically we're going to have observed. So in this one, we're going to have observed expected. Let's read this this one. Throughout this chapter, we have been compared the test of statistic hypothesis for single population parameters, mu, sigma, and p. Now we shall consider a test to determine if a population has specific theoretical distribution. The test is based on how good a fit we have a frequency of occurrence observation in our observed sample and expected frequency obtained from the hypothesis distribution. So basically, for example, if we roll a dice, we have observed value, but we expected all of them. We have 6 sides. Each side have 1 out of 16. So for example, x equals 1, x equals 2, x equals 3, x equals 4, x equals 5, x equals 6. So if I roll the dice 60 times, so basically I expect this n1 equals 10, n2 equals 10, n3 equals 10, n4 equals 10, and 5 equals 10, and 6 equals 10. This is what I'm expecting. That's equivalent for all of the 6 observations. But now if I have n1 equals 0, n2 equals 50, n3 equals 10, and 4 equals 0, and 5 equals 0, and 6 equals 0, what happened? It means this dice is not fairy dice. It only occurs at the second phase. Okay, so this is a way to test if it's a uniform distribution. For example, this is a uniform uniform on all 6 sides. Okay, so this is a way to test if the dice is fairly dice or not fair dice. Okay, we're gonna have example like this in your homework. Toss a die. You compare this 2020, 17, 18, 19. I think this is pretty nice observation. Even you have several observed values less than 20, but overall they're pretty close to 20. They'll be fine. Okay, like this example here, this is not a fair dice. Okay, so the goodness fit of test, we use chi-square. The formula is chi-square is I equals 1 to k, and O is observed, EI is expected value, square over EI. We use this formula to find out the chi-square value. There are two problems in the homework will ask you to find the chi-square using this formula to do it. Okay, which is not really hard. Okay, there's a formula to find out that expected value as well. Right, 10.12 is test for independence. So test for independence, which means it give you two data, ask you if these 2 columns of data are independent or not independent. Okay, so for example, okay, we still use a chi-square. For example, if a group of people, they get we're gonna say example in your homework. a group of data. Let me see. Let me see the homework problem. There's one which is really nice problem. Let me see. Okay, for example, in the experiment to study the dependence of hypertension on smoking habits, the data below, taking 179 individuals, test the hypothesis that the presence or the absence of hypertension is independent of smoking habits. So hypertension or non-hypertension, smokers, non-smokers have hypertension or non-hypertension. Moderate smokers, heavy smokers, you can see that we do see a pattern here. If they are independent, they all should be the same, like 2150. This next one should be 2150 as well, or 2550 something as well. But now the data tells us it's not, it's increasing. Non-smoker have less hypertension. Heavy smoke have more ratio of hypertension. So my common sense tell me it should not be dependent. It should not be independent, right? So this is a good way to test if something is independent of the other factor or not. So this in the statistics. You want to test if one factor is independent of the factor or not independent or not independent. Okay, so what do we do here? There is a formula. So still we have the chi-square equals observed minus expected value square over expected value, no square here. But then also the expected value we have of expected frequency is clone total multiply the row total. Okay, divided by the grand total. So this is the formula to find out the expected value. Observed values is always given to you. Okay, we are going to have an example to do that one in the homework, to use this formula and find the chi-square and find the probability. Find the chi-square, can find the p-value. If p is small, then non-hypothesis, reject non-hypothesis. P is high, then not rejected. Test for homogeneity. So this one, let me think. I think this one is the independence, a random sample. It is more. It's not just two samples. It's more of the sample. Okay. So we are basically interested in determining whether the three categories of voters are homogeneous with respect to their opinions concerning proposed abortion law. Such a test is called a test of homogeneity. Okay, homogeneous is basically they're all equivalent or they are the same. So now we're going to have three of them. For example, referring to data table 10.8. Okay, so let's read this whole problem again. When we test for independence, section 10.12, a random sample of 1,000 voters was selected, and the row and column totals are our contingency table determined by chance. Another type of problem for which the methods of section 10.12 applies to one in which either row or column tables are predetermined. Suppose, for example, that we decide in advance to select 200 Democrats, 100 Republicans, 150 Independents from the voters of the state of North Carolina, and record whether they are for a proposed abortion law against it or undecided. These are the data we have. So the null hypothesis is for each opinion, the proportion of Democrats, Republicans, and Independents are the same, homogeneous, right? So P1 equals P2 equals P3, or they're the same ratio or the same vote numbers. The non-alternative hypothesis, at least one opinion is different. At least one opinion, the proportion of Democrats, Republicans, and Independents are not the same. And the critical region is gamma square. V equals 4. So V equals n minus 1 times, well, you can use column. So C minus 1 times row. So R minus 1. We have three columns, 3 rows. So we got the V degree of freedom is 4. With the degree of freedom, we'll find the chi-square. Chi-square number is 1.53, which is less than when gamma equals 0.05, degree equals 4, then the chi-square is bigger than 9.44488. So now I use the formula chi-square equals OI minus EI square over EI. I use the formula to find the chi-square, which is 1.53. It's less than this critical value. If it's less than that, we do not reject it. Okay, there is not sufficient evidence to conclude that the proportion of Democrats, Republican, and Independents are different from each other. Okay, so test for several proportions will have the same way to do it if you use the same formula. Okay, so this is the basically the introduction of lesson 12. I hope you have already read all of this content and then did most of your homework. I'm going to next video. I'm going to introduce how to do the homework problems. Okay.